welcome you all. Now we are going to discuss about marine engines. So we know that in ship we have internal combustion engine. Our engines are at big size. So we are going to discuss about that engines deeply. So marine engines are required to operate continuously, rapidly, and safely in unmanned engine rooms, and with extended periods between plan overall. This may expect to operate of considerable periods at low power without ill effects, and to be tolerant of low quality fuel while maintaining very high thermal efficiency. Continuing development and improvement in design are necessary to meet these demands, and new generation of engine models are produced to take advantage of advance in research and experience. Considerable improvement in design and performance of turbochargers and charge air system in recent years have contributed substantially to increase in engine power and economy. The supply of charge air at reduced power is sufficient to maintain efficiency combustion, and at full power surplus essence, gas energy can be diverted to operate power takeoff system, which will supplement the main or electrical power output. Changes in world trade may lead to emergence of different ship types with special demand upon their power system. Manufacturers produce a range of cylinder sizes, and further sizes are developed when a particular demand becomes evident practically. Now we come to the chapter. Before that, we discuss of the introduction of engines. Now we know all that we have the slow speed engine and high speed engine. Now we discuss about the slow speed engines. Slow speed engines category refers to engines operating between 55 to 150 rpm. Large slow speed direct drive main engines operate exclusively on the two-stroke cycle and are cross-head construction, which allows complete isolation between the cylinders and the crankcase. They are best able to tolerate low quality fuels and both is successfully to obtain the highest thermal efficiency. Slow piston speed and fewer working parts make them very economically in lubricating oil and give low rates of fuel and remarkable reliability. Although there are now few manufacturers producing these engines, they dominate the market, particularly in ocean-going ships. The variety of size and numbers of cylinders are available to suit all power requirements. In addition to the standard model, they are produced in long stroke version with stroke bore ratio up to 3.8:1 and the speed down 55 rpm, allowing the use of large slow propellers for high efficiency in vessels such as bulk carriers and large tankers. Slightly slower, shorter engines are operating in speed range of 100 rpm are designed for high speed container ships. Short stroke models cater for ships with limited draft, propeller size or engine room height. Many of the basic engine components are common to all versions. Current models of two-stroke engines are illustrated here together with some older models which are still in operation and are distinctive feature of which students must be aware. Cylinder lines are alloy of cast iron. A stiff collar at the upper end resists the heavy gas load. These lines of the cylinder jacket is bore cooled with water flow rates regulated to maintain the correct temperature to the liner. The lower end is uncooled within the scan space. Multi-level cylinder lubrication is used to reduce the liner wear rates. The solid forged steel cylinder cover is bore cooled to reduce the thermal stress and to conduct the heat from the fuel injector package. A centrally positioned large exhaust valve cage has its valve seat intensely cooled, taking water from the cover. The valve is manufactured of pneumatic ATA alloy and is rotated by vanes fitted to its spindle. It is opened by the hydraulic pressure from a cam-driven actuator and is closed under the action of an air spring. The piston has an alloy steel core and has 5 compression rings fitted in chromium plated grooves. There is a sharp cast iron scale. The piston oil is cooled using the both shaker method and small jets to be propelled oil into boreholes close to the underside of the core and begin the ring grooves. Oil for cooling is supplied and returned through a bore piston rod from swinging links on the crosshead. The single piece crosshead has a piston rod bolted to each upper surface in the continuous full length lower of top end bearing, which is of white meat and lubricated with high pressure oil. Guide screws are attached to each end of crosshead. A small built-up crankshaft has slim welds to allow large bearing areas. Main bearing caps are secured by jack bolts from engine frames. The main camshaft is gear driver and is fitted with the servo motors to retain fuel pipe cams and the start distributor when operating the engine system. Fuel pumps are the cam driven for time type with a variable engine timing to adjust timing and maintain the efficient combustion at a low speed. Each pump supplies the three uncooled fuel injectors and placed symmetrically in each cover. Hot fuel oil supplies the valves and not ejecting. The engine has through scavenge and constant pressure turbocharging with a high efficiency. Uncooled turbocharger supplemented at very low speed by two constant speed electrical driven auxiliary air blowers. These have many similarity to the Series 2 engines which were developed from it. This engine has water cooled piston. Water is supplied and returned through telescopic glands. These are entirely separated from the crankcase to avoid any possibility of contamination. A separate piston cooling water circulation system is used. The crosshead has split top end bearings. The piston rod is attached to the central block of the crosshead between the two top end journals. Each bearing has flexible support to limit load concentration. These wall aluminum tin bearing cells are fitted. Now we are going to discuss about MAN BMW MC engines. MAN BMW K90 MC engine. This is a large Craftwork type two-stroke engine with a bore of 900 mm and 2300 mm stroke and an operating speed of 104 rpm. It is considered between 6 and 12 cylinder. Developed as one of extensive range of manufacture of MC engines. It is of the power and speed best suited of large, fast container ship. The increase in running speed is obtained by a slight decrease in engine stroke. High thermal efficiency is maintained by an increase in mean effective pressure. Construction can be considered generally as difficult for the whole range. The engine bed plate is of rigid boss form, fabricated from steel plates with main bearing supports of cast steel. Welded A-frames are assembled into a frame boss which contains the crankcase, the crosshead guides and also support the cell for the chain drive of the camshaft. A cast iron cylinder frame accommodates the scavenge space between the cylinder jacket and the diaphragm, both of which are water cooled. Long press test tie bolts are fitted between the top of the frame and the underside of the bed plate. The cylinder line is the alloy of cast iron. Its upper flange lands on top of the frame and has bore cooling. It is equipped by 4 sealed cylinder cover which is also bore cooled and is shaped internally to accommodate most of the combustion space. Cylinder lubricating oil is injected at the one level on the liner. Piston have a chrome molybdenum alloy steel with hard chrome surface ring grooves in which 4 compression rings are fitted. In this particular model, a protective layer of inconel is welded to the part of the chrome surface to prevent the high temperature corrosion. The piston is oil cooled, oil being supplied by a telescopic gland to the crosshead and then through the piston rod. It is the return from the crosshead to the starter pipe in the crankcase. A short cast iron slip is added. The chrome is bolted to the piston rod at the inner support ring. Surface hardening reduces wear on the piston rod at the diaphragm gland. The rod is bolted at the top of the cylindrical crosshead, which is in large diameter and incorporates a full length of bottom half bearing cell. Floating guide soles are attached at each end. The crankshaft may be either semi-built or of welded construction with a large journals and pin. All crankcase bearings are of white metal. Main bearings have thin wall cells. White metal belt is also used for guide surfaces. The exhaust valves are operated hydraulic under oil pressure from the cam time actuating piston. They have compressor air spring which allows them to be rotated by vanes. Fuel pumps are cam driven and timed by the plunger release. An adjustable barrel allows variable ignition timing to maintaining the combustion efficiency and lower speeds and can be adjusted to match the ignition quality of fuels. Pump time is changed for Aston operating by a link connected to the cam roller guide which is activated by a compressor air. Each pump supplies 3 identical fuel injectors for a corresponding unit. Injectors are uncooled, but they circulate hot fuel oil directly while their needle valves are in closed position. The engine operates with a constant pressure resistance system with uncooled turbochargers. 2 auxiliary flows are fitted to operate the low charge air pressure or at low engine revolution. A number of ways heat recovery and power takeoff system can be operated under running condition. Now we are going to discuss about BMW KEF engine. This engine produced up to 20 years ago, including many features which have been improved and developed in present models. Exhaust valves are operated by push rods, were closed by helical steel rings. This through scavenge was used and pulse exhaust system required grouping of turbocharger efficiency was moderate by present standard. Wet plates were fabricated on those same were cast iron. Semi-build-up connector and spilled crosslet bearing were used. Reversing was carried out with a large servo motor which rotated the whole camshaft to retain fuel pump and exhaust valve cam. Heavy fuel was used and it was necessary for fuel to have a separate cooling system. This engine have good service over many years. Sulzer R&D engine. This engine was produced in 1938. It showed many developed which are present in modern engine, particularly stage, a different philosophy in combustion chamber arrangement. No exhaust valve was fitted and exhaust timing was controlled by long distance curve which is controlled exhaust port in the center liner. This required in the form of a cross-loop scavenge. The close proximity of both scavenge and exhaust ports made line design more difficult and increased stress and wear in this area. Cylinder covers were in concentration water-cooled parts. The center section was a cast iron and contained the valve packet. The outer section formed a strong pack of a cast steel. In later model 4 steel, one piece covers with the bore cooling were introduced. A single central fuel injector was fitted. This was water-cooled for burning heavy fuel. Cam-driven or well-timed fuel pumps were used, and apart from the air stroke distributor, these alone were retimed for reversing. A servo motor rotated the main camshaft for this purpose. The bed plate was fabricated from steel plate with steel casting and main bearing support. Low stroke bore ratio allowed bed plate to more shallow with a strong longitudinal cross section at each side. Constant pressure exhaust system was used. With water-cooled turbocharger, charge air pressure was augmented by the system under piston charging. Many of these engines are produced for service support ships and for show plan. Now we are going to discuss about medium and high speed engine. Before we discuss this slow speed engine, now we are going to discuss about high speed engine. Most of these are designed to operate the 4-stroke cycle. Before know that slow speed engine is operated mostly in 2-stroke engine. Under a trunk piston construction, they are much lighter and smaller than equivalent slow speed engine, but requiring gearing or some other means to reduce the driven speed for ship propellants. Medium speed generally means between 400 to 1000 rpm. Smaller engines are robust and can be highly rated. Their power, weight and power size ratio make them particularly attractive where engine room size is limited. They also require less strength built into the ship supporting structure. The long-stroke version are produced to give greater fuel economy and heavy fuels. Medium speed engines are widely used in ferry-type vessels and those of limited size. Rapid progress has brought many different models into production and a wide choice existing size, speed and power. They are well adapted of re-entering the existing ship, fitting well into the existing engine space and giving ample power with increased economy. Flexible couplings and torsional vibration dampers are fitted other couplings between engines and gearbox drives. Plant system may incorporate number of similar engines of this type, giving great flexibility for part load operating or maintenance. With controllable pitch propellers, there is no need to fit the more expensive reversible engines. Modern engines can operate successfully on all but the heaviest of fuel with surprisingly low wear rates. Smaller and lighter parts with similar construction give easier maintenance, shell, bearing, and are in general use. Engines may operate on either pulse or constant pressure turbocharged system as four-stroke engine. They are self-aspirating and slow-speed pulse. Pulse charging will incorporate converters to reduce the size of the SR manifold and improve turbine efficiency. This system may have some advantage where rapid isolation is required. While constant pressure gives the greater efficiency overall, turbochargers may require water cooling with the high exhaust temperature which may be poor use. Medium and high speed engines may be constructed in either inline or V configuration, and many manufacturers supply all but the largest bore models in either form. As the name implies, the V engines are constructed with two banks of cylinders arranged at an angle of using common crankcase and braided with considerable saving in size and weight twice as many cylinders can be accommodated in given length. Although the width of the engine is increased due to the increased power from the engine, however, the crankshaft must be in adequate strength. A variety of methods have been utilized to connect the two pistons to each through the shaft. Most common is the side-by-side arrangement with two common bearings. The V formation gives economy in the common space used for exhaust system and turbochargers. Two camshafts are used, but in multi-cylinder engines, starting air valves may only be necessary on the back of cylinders. We are going to discuss about the engine cycles. The term cycles refers to one complete sequence of operations required to produce power in an engine. This cycle of operations is continuously repeated while the engine is running. For a diesel engine, it consists of four operations within the cylinder. That is, compression of charger, injection of fuel which then ignites, expansion of hot gases formed during combustion, expulsion of used gas to exhaust. The cylinder is then recharged with the air and the cycle is repeated. Diesel engine can be designed to complete the cycle once during each revolution, and this is termed as a two-stroke cycle. Or alternately, to take two engine revolution to complete the four-stroke cycle. An engine can only operate on the cycle for which it was designed. Engine stroke is measured as the full distance through which the piston moves between each end of its travel. It can be seen that it must move through two complete strokes, one up and one down, during each revolution of the engine. Engine timing refers to relative time or position of the crank, at which each operation during the cycle is commenced and is repeated. It is measured as the angle through which the crank has been rotated from a data position such as a top or bottom center. Now we are going to discuss about the two-stroke cycle. Particularly all large slow-speed direct drive marine diesel engine operation the two-stroke cycle. As its name implies, a two-stroke cycle takes place in two consecutive strokes of engine piston or one revolution of the crankshaft. Thus, each operation of the cycle is repeated during every revolution of the engine. The two-stroke of the cycle may be termed as compression stroke and power or expansion stroke. Operation takes place in the fixed order and must occur when the piston reaches the corresponding position in the stroke. These positions are shown as a volume or an indicator diagram which related them to the pressure of the cylinder. It is convenient to express them in terms of angle of crank position measured from top dead center or bottom dead center, and they may be shown as a circle in a timing diagram. Number have been added for reference. Actual timing may differ between the engine due to construction and design difference such as ratio of compressor and crank length, stroke bore ratio, engine speed, engine rating, etc. Completion of scaven, air is entering the cylinder, expelling the gaseous gas and recharging it for next combustion. Scavenge and exhausting are open. post scavenge. Scavenge ports have closed and other unsafe air within the cylinder may leak assessed. In some engines, 2 and 3 are made to coincide with the eliminate leakage of air. Now, 3 and 4 compression. The cylinder is now closed and the air trapped within the cylinder compressed by the upper stroke the piston to raise its temperature sufficiently to ignite the fuel. 4, 5, 6 stages. Fuel injection takes place and the combustion occurs, causing rapid rise in pressure. The period for which this continues depends upon the fuel setting power to be produced. Expansion. Combustion completed. The hot gases expand, forcing the piston downwards. The hot gases expand, force the piston downwards and converting the heat energy from combustion into work on the piston. The stage 7 to 8 exhaust program. Stage 8 to scavenge stage. Then loss again stage scavenging then continues for the next cycle. Same for the four-stroke cycle. The majority of the medium and high-speed diesel engine for main or auxiliary drive operate on the four-stroke cycle, which take place during 4 consecutive strokes or 2 complete rotations of the engine. The four-stroke may be compression stroke, power or expansion stroke. SR stroke and then aspirating or air injection stroke. Numbering the operation in the sequence of timing diagram. Now we are going to discuss about the indicator diagrams. An indicator diagram is a pressure volume graph taken from the pressure in the cylinder of a working engine. It is plotted as a continuous line showing all pressure changes during all complete engine cycle. Indicator diagrams can be a great assistance to the students understanding the operation of engine. Examination candidates are required to familiar with the information which may be obtained from the shape and dimension of the diagram. In many modern engines, sophisticated measuring device may be fitted to record cylinder pressure as an oscilloscope, trace and printer. Usually these are not complete course indicator diagrams and they are described later in this chapter. For some slow speed engine, it is possible to obtain indicator diagram from each cylinder by using an engine indicator. Now we will discuss the engine indicator. Briefly, this consists of spring-loaded piston and with the spring is compressed in proportion to the cylinder pressure acting. The piston moves a pin attached to the amp through a parallel link mechanism. A cord with sensitized surface is wrapped around the indicator drum. The indicator cord for the chosen cylinder is first blown through the clear liquid for carbon and the indicator is connected to it. The cord of the indicator drum is attached to some form of the engine stroke synchronizing mechanism for the crosshead or cam. The cord is now open and the indicator pin is held against the cord. The tracing of the diagram for one side of the engine, the pressure is recorded to the vertical side according to the stiffness of the indicator compression spring. Corresponding cylinder sweat volume is recorded on the horizontal scale due to rotation of the drum by its cord. By turning the indicator top to end position, a horizontal line represents the atmospheric pressure is on a diagram. This can act as the pressure turbine. 4 types of indicator diagrams can be obtained. These are illustrated for a 2-stroke engine. Power cord is taken with the indicator drum rotation in phase with piston movement. The area within this diagram represents the work done during the cycle of scale. This may be used to calculate the power produced the main indicator pressure of the cylinder. Irregularity in the shape of the diagram will show the operating faults. Maximum or peak pressure may be inserted the scale between the atmospheric line and the highest point of the diagram. Power cords of 2-stroke and 4-stroke cycles are explained. Vertical to relate the corresponding timing diagrams. It can be seen that 4-stroke cycle pressure changes are so low during the last 2 strokes and this appears as a straight line. Compression diagram is taken in similar manner to the power cord but with the fuel set off from the cylinder. The height of this curve shows the maximum compression pressure. Compression expansion lines credentials note that the indicator is correctly synchronized with the engine. Reduction in height of this diagram shows the low compression which may be due to one cylinder liner, faulty piston, insufficient scavenge air, or leakage as well. Any of which will cause poor consumption. Draw cord or out of phase diagram is taken in similar manner to the power cord with the fuel pump engaged with the indicator drum 90 degree out of phase with the piston stroke. This illustrates more clearly the pressure changes during a fuel combustion, fuel timing, or injector fault may be detected from its shape. Right or weak spring diagram is again similar to the Parker phase with the engine, but taken with the line compressor spring fitted to the indicator spring. Pressure changes during exhaust and scaling should be enlarged. It can be used to detect faults. It can be used to detect faults in this operation. Irregularity in the diagram. Some irregularity in the shape or detail illustrate the incorrect engine operation. If the some fault appears on the diagram from all cylinders, the cause must be general one with the fuel condition or supply. Turbocharger system and the engine cooling are E or O incorrect camshaft timing. Indicated diagram shafted by some of the more common faults are illustrated. Fuel ignition timing provided the fuel and engine temperature are correct and the injector is operating normally. The time between the injection of the fuel and ignition is almost constant. Consequently, ignition timing falls signify the corresponding timing fault in the injection. They will affect the shape of the power diagram, but are far more easily detected and on-phase diagram. Early ignition. This will cause an abnormally high peak pressure in the cylinder at about the top of the piston stove. Heavy shock load is will transmitted to the running gear and bearing with the corresponding locking zone. Although the thermal efficiency is high and exhaust temperature reduced to a shock load and constant vibration may cause damage. Cause of early ignition may be incorrect fuel timing, broken or wrongly set injector springs, incorrect fuel conditions, or overheating of parts within the cylinder. Late ignition. It can be seen. This causes a low peak pressure which occurs at the top of the center of the piston. Power is lost since the fuel is not brought correctly to transmit power at the most effective part of the stove. Combustion may continue during the expansion stove, see after burning, and may be incomplete, giving loss in the energy produced high exhaust temperature and smoke. Late ignition may be due to excessive injector spring setting, poor atomization, high viscosity or poor quality fuel pump leaking or incorrect time. Low compressed, insufficient supply of compression air or undercooling of parts within the cylinder. After burning, this occurs to slow or late combustion of fuel during the expansion stove of the piston and is shown by the rise in expansion line during the later part of the stove. Exhaust temperature and pressure will be high, with the burning fuel and carbon passing to exhaust. This may burn exhaust valves and foul the exhaust system, with the risk of turbocharger surging or uptake fires. High temperature within the cylinder causes degradation in lubrication and possible damage to the liner surface and piston rings. There may also be the burning of the piston pump. Then, leaking fuel injector. This can be detected by a loss in power in the updated cylinder together with the smoke at exhaust and high exhaust temperature. There may also be non-power pressure wave in the injection system. An indicator diagram taken from this cylinder will show fluctuation of the pressure during the expansion process due to secondary burning of fuel leaking from the valve. A high expansion line at the exhaust opening indicates after burning. Loss in power will be due to incorrect combustion since the fuel pressure wave from the fuel pump and must fill the space left by fuel leak from the injector. This may also cause hot gas from the cylinder may blow back into the injection tip, forming the carbon and choking the atmosphere. Carbon may also form on the outside of the atomizer due to burning of the triple of the fuel. The injection should be changed and tested to reduce the possibility of the leaking injection, and good maintenance of the fuel pouch injection should be carried out with routine changing of the injector. Fuel must be purified and filtered and must be supplied at the correct temperature, and fuel injector must also be maintained at the correct temperature. Partly choked fuel. This may be due to the contamination of the fuel in which debris may choke at the small atmosphere hole in the injector. Alternatively, it may be caused by a leak injector allowing hot gas to blow back into the injector, causing carbon to form and choke the injector. Overheating of the injector nozzle may also cause buildup of carbon. There will be loss in engine power. There will probably be a hammering the fuel pipes between the fuel pump and injector, and this may lead to rupture of fuel pipe. A choke valve can be controlled by the indicator power and droppers and reduce exhaust temperature. The remedies to change the fuel injector, clean the fuel system, ensure correct centrifuging and filtering of fuel, and maintain the correct fuel balance temperature. Low compression. Now we are going to discuss the low compression and the low compression. This one is the low pressure and the compression diagram. It is quotable that first evidence was from faulty compression. Low pressure may be due to lack of air being supplied, turbocharger fault, choke, scavenge ports, or inlet fault, etc. Now we know that the blow pass is then usually detected during the expansion stove. Blow pass is a term used when the combustion gases at high temperature leak past the piston between the piston ring and the cylinder liner. This will cause a rapid local overheating, ruining the lubricating oil film and cause the further damage to the surfaces and possible piston seizure. Burning gas will enter scavenge spaces into tools for causing cooling, overheating, and even scavenge fire. In the four-stroke trunk piston engine, these gases will enter the crankcase with the severe risk of the crankcase explosion. Blow pass may be caused by the SSC cylinder liner wear, lack of the cylinder lubrication, one broken, stuck, or poorly maintained piston tails. Wound piston ring groove landings allowing rings to caught and jam. Carbon jamming rings in grooves, it will be aggregately if the engine is overloaded. The remedy is to cage the cylinder liner, renew if necessary. Overall piston clean ring, grooves and cage. Machine or fit new groove insert as necessary. And renew piston rings with the correct clearance. Maintain cylinder lubrication and avoid overloaded. Exhaust valve opening. Exhaust valve opening on a slow running engine can be checked by means of light speed indicator diagram. This will not give an accurate time check, but by comparison with normal diagram or one taken during the original engine trials, be seen if valve opening is early or late. Early opening of exhaust valve will cause loss in power since pressure is released too soon. It will give a high exhaust temperature with risk of overheating and contamination. Late opening will reduce the scavenge efficiency by reducing blowdown. It will also affect the supply of energy to the turbocharger. Choke pressures. The pressure during the valve opening does not fall as rapidly or as fast as it should and prevents the correct blowdown and recharge of the cylinder with air. It causes loss in power and high exhaust temperature, smoke and possible surge in the turbocharger, and this result the contamination due to incorrect combustion of excessive cylinder lubricating oil. Power balancing of engine. For economic and efficient running of an engine, equal power should be produced from each cylinder. This is then said to be power balance and may be necessary to make some minor adjustment to achieve this. Power produced is related to the quantity of fuel injected and balancing is carried out by small adjustment to individual fuel pump controls. Adjustments are limited to ensure units are not overloaded, exhaust temperature are not excessive, and then pump controls still cut off and brought to stop. Fuel pump air position and exhaust and cooling return temperature from each cylinder should be noted. Equal exhaust temperature on their own do not necessarily show an accurate balance, particularly in turbocharged engine. Figures 2, however, tend to give some indication of balance when they follow a pattern similar to that recorded at display trials. Power balancing can be checked by the measure from indicator diagram by calculating the area or mean height from each cylinder. For medium, a high-speed engine it may be impractical to use normal engine indicator due to high velocity of force causing vibration in the spring or drive mechanism. If other mean are not available, power engine may be related to peak or maximum pressure in the cylinder. Some manufacturers recommend that the ignition pump. The difference between the peak pressure and the maximum compressor pressure of each cylinder may be used to check the power balance. A number of assumptions have to be made regarding the operating efficiency of the engine. In order that this can be justified, it is particularly important that regular and correct maintenance is carried out of the engine, and that any deviation from normal running is noted, investigator corrected the earliest opportunity. Fuel injection equipment is particularly important and fuel pump settings, clearance and timings must be checked and maintained during periods. The engine is out of service. Fuel injector must be changed regularly, cleaned and tested to ensure trouble-free operation. The injector is most likely part of the system to be subjected to fault in service. A fault in one injector will cause loss in power and affect the cylinder, but may also mean that the other cylinders are subject to overloading as the engine governor attempts to maintain normal total power speed. If an engine operates in an unbalanced condition, some bearings and radiator may become overloaded. This may cause overheating and bearing failure. Overloading in cylinder may cause piston to pause, with corresponding dangers of overheated or seized piston. Unbalance will also set up for vibration, which, if maintained in prolonged period, will cause fatigue from the fluctuating stress engine. This may in turn lead to fatigue cracking of metal bearings, fracture of bearing struts or close, cracks in camshaft and vibrate, and slacking or failure of holding downwards. The watchkeeper may setting that running condition are normally by observation of the relevant temperature and pressure, particularly exhaust and cooling return temperature, lubricating oil and turbocharged pressure. The exhaust should be clear of smoke and there should be no unusual noise or vibration. We discuss about the combustion monitoring. Modern measuring instrument and recording equipment make it possible to monitor all necessary pressure, speed, temperature and even wear rates within an engine. By connecting a pressure sensing transducer to the indicator curve, it is possible to record the pressure in the cylinder continuously. Pressure can be plotted on an oscilloscope traced to horizontal scale of time or corresponding crank angle. A printout of this diagram appears comparable to an accurate constant-based scale of toss-based diagram. Other important points such as top center position, point of fuel injections can be superimposed. Peak and compression pressure can be seen and equated for power balance. Combustion monitoring may be used to maintain the efficient condition and the fuel of different qualities we use. Model diagrams should be made for the engine during stop testing and initial driver selection. This can be compared to subsequent working tests. Next, gas exchange process. Scavenging. In an internal combustion engine, this is removal of exhaust gas from the cylinder after the combustion and it is replacement with the air for subsequent combustion. Efficient scavenging is necessary for good combustion and it is required for the very first working cycle of the engine. The passage of scavenged air will also assist cooling of the cylinder, piston and valves. Scavenge of four-stroke engine. This is carried out mainly by the pumping action of the piston during the two of its stroke. The piston expels the exhaust gas on its upward stroke and draws in the air of a subsequent downstroke. The scavenge diagram shows that there is a period of overlap during which the exhaust and inlet valves are both open together, provide the turbocharged supply air at a pressure greater than it in the exhaust manifold. A flow of cooling air will pass through the cylinder during this period. Scavenge is positive and very efficient, even in very high-speed four-stroke engine. Scavenge of two-stroke engine. Two-stroke rely on the charge of scavenger under sweeping through the cylinder and spilling the exhaust gas in front of it. This process must make place while both scavenge and exhaust connection are open, and the piston is near the bottom of the cylinder. Even in the slow running engines, this allows only very short period of the time for scavenge to complete. Some missing of air and gas will occur, but this must be kept to minimum volume. The exhaust passing to the exhaust system, the scavenger in two-stroke engine must be supplied to the cylinder at higher pressure than that in exhaust manifold. In modern engine, this is provided from exhaust gas driven turbocharger. The air being cooled to increase its density and cooling capacity. Earlier, two-stroke engine used variety of methods to supply scavenger These include the use of reciprocating pumps, rotary blowers, and compression from the underside of the piston on its downward stroke. All this added to the maintenance work absorb part of the power produced by the engine and were only able to supply the limited quantity of excess air. In large slow running engine, the air enters the cylinder through the circumferential groove of scavenge port cut in the liner and uncovered by the piston as it moves towards the bottom of stroke. They are closed at a symmetrical time on the falling of stroke. The discharge valve must open before pores are uncovered to allow the period of blowdown. Blowdown is the release of gas pressure at the end of the expansion as the gas valve opens. Gas passes to the manifold, carrying its remaining energy to the turbocharger. Cylinder pressure drops rapidly to the valve groove that in the scavenge trunk, allowing the fresh surge of the air to enter. There are three basic methods of scavenging within the cylinder, that is loop scavenge, cross scavenge, and uniflow through scavenge. Loop scavenge is which the air passes over the piston chrome and rises from the loop within the cylinder, expelling gas through the exhaust ports cut in the same side of the liner above the scavenge port. Cross scavenge, where the air is the directed approach, passing under the cylinder cover and down opposite side, expelling gas through the exhaust port other side. Uniflow through scavenge with the air passes straight up through the length of the cylinder, forcing the exhaust through ports or valves at the top of the cylinder. In all, this volume or direction of the air is ascertained by the port edges being angled in one or two places and by the shape of the piston crown. In case A and B piston skirt are at such angle will be necessary to prevent scavenge air leaking to SR piston is the top of its tube. KC tends to give higher scavenge efficiency with least mixing of the air and gas. It may also be used with greater temperature gradient between adjacent scavenge and exhaust ports, or the temperature difference on opposite side of the piston and rings. Uniflow or through scavenge with a large and centrally positioned exhaust valve is used in most modern slow-speed large engines. It allows design of efficient non-stroke engine and is less susceptible to damage from the products of combustion from low quantity heavy fuel. Absence of exhaust ports allow the liner to be simple construction, non-piston screws are not necessary and cylinder lubrication satisfactory mechanically. The swirl imparted by the port edges cause the air to rotate as it rises through the cylinder. The scavenge air trunk forms part of the engine structure and must be sufficient size and shape to supply even a quantity of air at constant pressure to all cylinders. It must be maintained in clean condition, be regularly inspected, pressure relief valves are fitted for safety. Turbocharger system. Most modern engines are turbocharged to increase the power output and efficiency with only relatively modern increase in size, weight, and initial cost. The efficiency of the system is increased by fitting the charge air cooler after the compressor. This will the air constant pressure increasing intensity before supply chain it for compression and the engine cylinder. The mass of the air pressure cycle can now be increased and the quantity of the fuel injected can be raised to give corresponding increase in engine output and thermal efficiency. Exhaust gas from the cylinder operates of the gas turbine, giving up the sum of its heat energy to do so. The turbine drives directly coupled air compressor which draws air from the atmosphere, compressor it then cools it in the charge air cooler before supplying to the engine through scavenge port. The turbocharger is free running at any engine speed. The exhaust gas energy must cause the turbine to run at stable speed at which the compressor will supply the correct mass of air to the engine. It is then said to be matched to that engine and it must remain matched over the full main operating power range. When an engine has two or more turbochargers operating parallel, they must all be matched. Match system may become unstable and surge if fouling or damage occurs. Turbocharger system may be designed to operate on either the pulse or the constant pressure exhaust system. Pulse system. The main engine to power the turbine in the system is derived from the pulse or impulse energy in the pressure wave formed during the blowdown from each cylinder. These waves travel through the manifold to the turbine nozzle where they are converted to kinetic energy at high velocity to rotate the turbine blades. This system gives rapid buildup of the turbine speed when an engine is started or maneuvering. To maintain the pulses exhaust connections are of limited diameter, no sharp ends are used and the turbocharger is fitted close to the engine. The peak pressure in the pulse waves may be higher than the pressure in other cylinders whose exhaust valves are open to prevent air backflow into this. That it is necessary in multi-cylinder engines to divide the exhaust between the number of manifolds of each connector to separate the nozzle box at the turbine. Up to 3 cylinders can be used each manifold without interference depending on their firing order. A divided exhaust system reduces turbine efficiency and may require more than one turbocharger per engine. The use of pulse converter in modern engines allows the individual cylinders to exhaust through common manifold, giving higher turbine efficiency and more compact system which allows the rapid acceleration when maneuvering.